Part 4. The People Behind the Numbers. A Historical Companion. A Preface. For the listener. Dimensionless numbers can sound, at first hearing, like a procession of Greek letters and unfamiliar surnames carried into the classroom by tradition. Reynolds, Mach, Froude, Weber, Prandtl, Nusselt, Sherwood, Damköhler, Deborah. The roll call is long, and to a new listener the names can feel detached from the physics they represent. This companion chapter restores some of that human and scientific context. It asks 3 connected questions. Who were these people? What problems were they trying to solve? And how did their names become associated with physical ideas that engineers still use? The account is deliberately selective. It is not an exhaustive history of every named dimensionless group. Instead, it follows the people and ideas most relevant to the scientific path of this audiobook, giving more time to the stories that illuminate fluid mechanics, transport phenomena, interfacial flow, and rheology most clearly. The story begins before dimensionless numbers were recognized as a distinct language. Leonhard Euler helped make fluid motion a mathematical subject. Joseph Fourier gave physical dimensions a systematic place in mathematical physics. During the 19th century, experiments on ships, pipes, wires, heat, and liquid surfaces revealed recurring relationships that could be expressed independently of a particular system of units. Lord Rayleigh made dimensional reasoning operational. A sequence of mathematicians and physicists developed the theorem now associated with Edgar Buckingham. Ludwig Prandtl then showed how a short physical argument could transform an entire discipline. From there, the language expanded into heat transfer, mass transfer, chemical reaction engineering, multiphase flow, and rheology. Part 1. Before the numbers, Euler and Fourier. Long before engineers spoke of dimensionless groups, Leonhard Euler helped give fluid mechanics its mathematical form. Born in Basel in 1707, Euler spent much of his working life in St. Petersburg and Berlin and became one of the most productive mathematicians in history. In fluid mechanics, his name is attached to the equations of motion for an inviscid fluid. Those equations describe how pressure and inertia govern motion when viscous stresses are neglected. The Euler number compares pressure forces with inertial forces. Its name acknowledges Euler's foundational place in the mathematical description of fluid motion, but it should not be taken to mean that Euler alone created dimensional analysis. Ideas about comparable quantities and dimensional consistency have a longer history. The modern language of physical dimensions becomes clearer with Joseph Fourier. Fourier was born in Auxerre in 1768, joined Napoleon's scientific mission to Egypt, later served in French public life, and published Théorie analytique de la chaleur in 1822. That work established the mathematical theory associated with heat conduction and gave physical dimensions an explicit, systematic role. A physical equation could not depend for its validity on an arbitrary choice of units. Its terms had to remain dimensionally consistent. The number bearing Fourier's name is dimensionless time for diffusion. It compares the time available for diffusion with the time required for a diffusive effect to cross a chosen length scale. At small Fourier number, the disturbance has penetrated only part of the domain. At large Fourier number, diffusion has had more time to act. The name connects the number to the heat conduction framework that Fourier helped establish. Part 2. Experiments that revealed the ratios. Heat conduction also brings Jean-Baptiste Biot into the story. Biot, born in Paris in 1774, worked across several areas of physics. His early work included the analysis of heat conduction and the difficulty of accounting for heat exchange at a surface. The modern Biot number compares resistance to conduction within a body with resistance to convection at its boundary. When the number is small, internal temperature differences may be small enough for a lumped temperature model. When it is large, internal gradients cannot be ignored. Biot's connection to the modern number is therefore indirect, but it lies within the history of the question the number answers. Fourier supplied mathematical theory. Jean-Claude Eugène Péclet carried heat analysis toward engineering application. Born in Besançon in 1793, Péclet wrote about heat in buildings, furnaces, and practical equipment. The Péclet number was named after him later. It compares transport by bulk motion with transport by diffusion. In a reactor, a channel, or a heat exchanger, it asks whether material or energy is carried mainly with the moving fluid or spreads, mainly through molecular diffusion. Particles bring another time scale into the story. How quickly they adjust when the surrounding flow changes. That question leads to George Gabriel Stokes. Born in County Sligo in 1819, Stokes developed major results in viscous fluid mechanics and served as president of the Royal Society. In 1851, he derived the drag on a sphere moving slowly through a viscous fluid, under the creeping flow conditions now associated with Stokes drag. The Stokes number compares a particle's response time with a characteristic time of the surrounding flow. A particle with a small Stokes number adjusts quickly and tends to follow the fluid motion. A particle with a large Stokes number retains more of its own momentum and may cross streamlines, strike a wall, or separate from the carrier flow. The common particle response time used in this number is built from the drag relation associated with Stokes. Similarity then moved from particles to ships. William Froude, born in Devon in 1810, worked on ship resistance and model testing. At Torquay, he developed a purpose-built towing tank in which ship models could be tested under controlled conditions. His work showed that geometric similarity alone was not enough. To reproduce the wave-making behavior of a full-size vessel, the model speed had to be scaled with the square root of gravitational acceleration multiplied by length. That relationship became the Froude number, although Froude himself did not use the modern term. It compares inertial effects with gravity effects and remains central to ships, rivers, spillways, hydraulic jumps, and other free surface flows. His son, Robert Edmund Froude, continued the family's work in ship testing, extending an experimental tradition across 2 generations. Natural convection brings in Franz Grashof, born in Dusseldorf in 1826. Grashof spent time at sea before becoming a professor of applied mechanics and a founder of the Verein Deutscher Ingenieur, the Association of German Engineers. The number bearing his name compares buoyancy with viscous resistance. It helps determine whether density differences caused by heating or composition can drive significant fluid motion without a pump or fan. The most visually memorable experiment in this part of the story belongs to Osborne Reynolds. Born in Belfast in 1842, Reynolds trained in mathematics and engineering and became the first professor of engineering at Owens College in Manchester. His practical experience included shipbuilding and civil engineering, but his lasting contribution came from asking why water in a pipe sometimes moved in a steady, orderly way and sometimes became irregular. In 1883, Reynolds introduced a thin filament of dye into water flowing through a glass tube. At low flow rates, the filament remained distinct. At higher flow rates, it became unsteady and mixed into the surrounding water. The change made the transition between what are now called laminar and turbulent motion visible to the eye. Reynolds showed that the behavior depended on a combination of velocity, pipe diameter, density, and viscosity. His paper, received and read by the Royal Society on March 15, 1883, and published later that year, described both the experiment and the broader physical criterion. The transition occurred near a Reynolds number of about 2,000 in his apparatus, but this value is not a universal switch. The onset and persistence of turbulence depend on disturbances, inlet conditions, geometry, and how transition is defined. The dimensionless group did not immediately carry its modern name. In 1908, Arnold Sommerfeld used the German expression Reynoldsische Zahl, meaning Reynolds number, in work on hydrodynamic stability. That documented usage became part of the terminology that spread through fluid mechanics. Later engineers, including Moritz Weber, helped organize and promote the broader language of dimensionless criteria in model testing. Reynolds made transition in a pipe visible. Ernst Mach made rapid pressure disturbances visible. Mach was born in 1838 near Brno, then within the Austrian Empire. He worked both as an experimental physicist and as a philosopher of science. His optical studies produced pioneering images of shock waves around high-speed projectiles, revealing phenomena too fast for direct observation. Mach number compares the flow speed with the local speed of sound. It tells the engineer whether pressure information travels much faster than the flow, or whether flow and acoustic disturbances move on comparable timescales. As Mach number rises, compressibility becomes increasingly important. Choking and shocks may appear under appropriate conditions, but Mach number alone does not guarantee a shock. Geometry, boundary conditions, and the way the flow is compressed also matter. A wire humming in the wind provides the next scene. Vincent Strouhal, born in 1850 in what is now the Czech Republic, studied the tones produced when air moved past a stretched wire. In 1878, he reported a systematic relationship among the sound frequency, flow speed, and wire diameter. Written in dimensionless form, that relationship becomes the Strouhal number. Frequency multiplied by a characteristic length and divided by velocity. The same number now appears in vortex shedding from cylinders, oscillating flows, and unsteady aerodynamic and hydrodynamic forces. The sound of a wire and the vibration of a heat exchanger tube belong to the same physical family. At a liquid surface, the balance changes again. Laurent Eötvös, born in Pest in 1848, is widely remembered for precision work in gravitation, but he also studied the surface tension of liquids and its variation with temperature. The Eötvös number compares gravity with surface tension. Small values indicate that surface tension strongly controls shape. Larger values indicate a greater role for gravity. A closely related or equivalent form is commonly called the Bond number, depending on the convention used. The 19th century ends with a method that could organize such relationships systematically. John William Strutt, the third Baron Rayleigh, was born in 1842 and received the 1904 Nobel Prize in Physics for investigations associated with the discovery of argon. For this chapter, his importance lies in dimensional reasoning. In The Theory of Sound, published in 1877, Rayleigh used a method in which a physical quantity was represented as a product of relevant variables raised to unknown powers. Dimensional homogeneity then determined those powers. Fourier had made dimensions explicit. Rayleigh made the method practical. Part 3. The Pi Theorem, a grammar for dimensional analysis. The theorem, now called the Buckingham Pi Theorem, was not created in one step by one person. Rayleigh's method helped establish the practice. Joseph Bertrand published a proof for restricted cases in 1878. Aimé Vachy gave a general formulation in 1892. A. Federman and Dmitry Ryabuchinsky published related formulations in 1911. Edgar Buckingham's 1914 paper then provided an influential treatment and introduced the symbol pi for the dimensionless groups. Buckingham, born in 1867, studied at Harvard and Leipzig, and later worked at the United States National Bureau of Standards. His paper, On Physically Similar Systems, explained how a physical relationship involving many dimensional variables could be rewritten in terms of a smaller set of independent dimensionless groups. The theorem does not solve the physics by itself. It does something more fundamental. It identifies the form in which the physics must be expressed. Experiments performed at different scales can be compared through the same dimensionless groups. Variables that appear separate in dimensional form become parts of a smaller set of physical competitions. The history matters because it shows how science often develops. A useful theorem may accumulate through restricted proofs, practical methods, notation, and later synthesis before one name becomes attached to it. Part 4. Boundary Layers and a Modern Engineering Language. On August 12, 1904, at the Third International Congress of Mathematicians in Heidelberg, a 29-year-old professor named Ludwig Prandtl gave a presentation lasting about 10 minutes. Its title was On Fluid Motion with Very Small Friction. In that short presentation, the boundary layer concept entered modern fluid mechanics. Prandtl's insight was physical, before it was mathematical. In a low viscosity fluid, viscosity need not be equally important everywhere. Its effects can be concentrated in a thin layer next to a solid wall, where velocity changes rapidly from the wall value to the outer flow value. Outside that layer, an inviscid approximation may remain useful. Inside it, viscosity governs shear, separation, and the connection between the wall and the surrounding motion. Born in Freising in 1875, Prandtl became one of the central figures of 20th century fluid mechanics. His boundary layer idea reconciled much of the apparent conflict between inviscid theory and the drag, separation, and dissipation observed in real flows. A small viscosity could have a decisive effect because it acted through steep gradients in a narrow region. Prandtl reorganized momentum transport near a wall. Ernst Nusselt carried dimensionless reasoning into convective heat transfer. Nusselt was born in Nuremberg in 1882 and trained as a mechanical engineer. In his 1915 paper, The Basic Laws of Heat Transfer, he used dimensional analysis to establish the functional form of convective heat transfer relationships. Limited experiments could then be interpreted and compared through dimensionless groups rather than as isolated apparatus-specific results. The Nusselt number compares convective heat transfer with conduction through a corresponding fluid layer. A value of 1 represents transfer no greater than conduction across that reference layer. Larger values indicate enhancement associated with fluid motion. The number became one of the central organizing quantities of heat transfer engineering. Moritz Weber belongs here because he helped organize similarity as an engineering practice. Born in 1871, Weber became a professor of naval mechanics at the Technische Hochschule Charlottenburg in Berlin. The Weber number bearing his name compares inertia with surface tension and is central to jets, droplets, sprays, and wave breakup. Weber's historical role should not be confused with Sommerfeld's documented use of the term Reynolds number in 1908. Weber's contribution was broader. He promoted the systematic use of dimensionless criteria, including Reynolds and Froude criteria, in engineering model studies. He helped turn similarity from a collection of individual rules into a more organized engineering language. Part 5. Transport interfaces and the multi-phase era. As the language moved into mass transfer, Ernst Schmidt's name became attached to the ratio of momentum diffusivity to species diffusivity. Schmidt was born in 1892 and became an important figure in German engineering thermodynamics. The Schmidt number plays for mass transfer a role parallel to that of Prandtl number in heat transfer. It tells the engineer how rapidly momentum spreads compared with molecular species. At high Schmidt number, momentum penetrates farther than mass over a comparable time, leaving a relatively thin concentration boundary layer. At low Schmidt number, species diffusion is comparatively rapid. The number helps connect flow conditions to concentration gradients near walls, particles, droplets, and interfaces. The breakup of a liquid jet presents a more complicated competition among viscosity, inertia, and surface tension. Wolfgang von Ohnesorge made that competition visible with high-speed cinematography. Born in Potsdam in 1901, Ohnesorge studied mechanical engineering in Berlin after initially considering music and art history. His doctoral work examined droplet formation and the breakup of liquid jets. In work published in 1936, Ohnesorge distinguished several regimes, from dripping and orderly jet breakup to wavy breakup and atomization. He organized the transitions with a dimensionless group, denoted Z in his work, that combined viscosity, density, surface tension, and a characteristic length. The group was later named the Ohnesorge number. In modern notation, it measures viscous influence relative to the combined effects of inertia and surface tension. Ohnesorge did not follow a conventional academic career, but his number became central to spray science, atomization, inkjet printing, and other processes in which liquid threads and droplets form or break. Part 6. The capillary number. A genealogy rather than a biography. The capillary number differs from most names in this chapter because it is named for a phenomenon, not a person. Its history is therefore a genealogy of an idea. The recorded history of capillarity reaches back to Renaissance Italy. Leonardo da Vinci noted that water could rise through narrow passages, even against gravity. His observation belonged to a wider investigation of water, motion, and natural form, but it did not yet provide a mathematical theory of the effect. The problem remained unresolved for generations. In 1660, Robert Boyle reported experiments showing that liquid still rose in a narrow tube when the pressure above it was reduced, indicating that ordinary atmospheric pressure was not the full explanation. Later experiments by Francis Hauksbee and James Jurin clarified how the height of the rise depended on the narrowness of the passage. The decisive theoretical step came in 1805. Thomas Young in Britain and Pierre-Simon Laplace in France developed complementary accounts of capillary forces and curved liquid surfaces. Their work established the foundation of the pressure relationship now expressed through the Young-Laplace equation. The viscous deformation of droplets brings the story to Geoffrey Ingram Taylor. Born in London in 1886, Taylor became one of the most influential fluid mechanicians of the 20th century. In his 1934 paper, The Formation of Emulsions in Definable Fields of Flow, he studied how droplets deform in controlled viscous motion. His apparatus allowed the competition between applied viscous stress and interfacial restoring stress to be examined systematically. That competition is expressed by the modern capillary number. At small values, interfacial tension strongly resists deformation. At larger values, viscous stresses can stretch a droplet and may contribute to breakup, depending on viscosity ratio, flow type, and other conditions. Taylor did not give the number its modern name, but his work made the ratio operationally central to droplet deformation. The terminology and notation became standard through later work on interfacial flows, emulsions, coating, porous media displacement, and enhanced oil recovery. The precise first use of the modern name and symbol is not assigned here because the available evidence does not support a single definitive origin. What can be stated securely is that no one person owns the capillary number. Young and Laplace established the pressure physics of curved interfaces. Eötvös contributed to the study of surface tension. Taylor made viscous droplet deformation experimentally concrete. Later engineering communities turned the ratio into a standard working tool. Part 7. Heat, mass, and chemical reaction. Chemical engineering expanded the dimensionless vocabulary by placing reaction and transport in direct competition. Gerhard Damköhler, born in 1908, worked in chemical reaction engineering at Göttingen. He died in 1944 at the age of 36, leaving a body of work that helped establish how chemical kinetics should be considered together with flow, diffusion, and heat transfer. Damköhler number is not one unique formula, but a family of ratios. Each compares a characteristic reaction rate or reaction time with a characteristic rate or time for transport or flow. A small Damköhler number may indicate that material leaves a system or spreads through it before much reaction occurs. A large value may indicate that reaction is fast enough for mixing, heat transfer, or mass transfer to become limiting. The exact definition must therefore match the process being analyzed. Heat and mass transfer become parallel through Thomas Kilgore Sherwood. Born in 1903, Sherwood spent much of his career at the Massachusetts Institute of Technology and became a major figure in chemical engineering. The Sherwood number is the mass transfer analog of the Nusselt number. It compares actual convective mass transfer with a reference rate based on molecular diffusion. This parallel is more than a resemblance in notation. Many mathematical structures recur across momentum, heat, and mass transfer. A heat transfer correlation written with Nusselt, Reynolds, and Prandtl numbers may have a mass transfer counterpart written with Sherwood, Reynolds, and Schmidt numbers, provided the physical assumptions and boundary conditions support the analogy. A different comparison is needed when heat and species diffuse simultaneously. Warren Kendall Lewis, born in 1882, became a foundational figure in modern chemical engineering and in the organization of processes through unit operations. The Lewis number compares thermal diffusivity with mass diffusivity. It matters in drying, evaporation, combustion, humidification, and other processes in which temperature and concentration fields develop together. Part 8. Memory and Time. Weissenberg and Deborah. Some fluids carry a memory of deformation. This brings Carl Weissenberg into the narrative. Born in Vienna in 1893, Weissenberg became associated with a striking demonstration of viscoelasticity. When a rod rotates in an elastic polymer solution, the liquid can climb the rod instead of moving outward as a simple Newtonian liquid would. The phenomenon is known as the Weissenberg effect. The Weissenberg number is formed by multiplying a material relaxation time by a characteristic deformation rate. It indicates whether the material has time to relax while the flow is deforming it. When the number is small, relaxation is relatively rapid. When it is large, elastic effects can persist through the deformation. The exact definition depends on the flow and on the characteristic rate selected. The Deborah number asks a related but distinct question. It was introduced by Marcus Reiner, an engineer born in 1886, who helped establish rheology as a named field with Eugene Cook Bingham. The word rheology was adopted from the Greek idea expressed by Heraclitus: everything flows. In August 1963, Reiner delivered an after-dinner talk at the 4th International Congress on Rheology in Providence, Rhode Island. The talk was published in Physics Today in January 1964 under the title, The Deborah Number. Reiner argued that the statement, everything flows, is incomplete unless the time of observation is specified. He drew the name from the Song of Deborah in the Book of Judges and quoted the image, "The mountains flowed before the Lord." The physical point was that even a mountain may flow over a time scale far beyond ordinary human observation. Reiner defined the Deborah number as relaxation time divided by observation time. If the observation time is long compared with the relaxation time, the material has time to flow. If the observation is short or relaxation is slow, the same material may appear more solid-like. Deborah number therefore emphasizes the relationship between material time and the time scale over which the material is observed or processed. It is unusual among major dimensionless numbers because it is named not for a scientist, but for a female figure in a biblical text. A closing note: the names in this selective history now carry more than formulas. Reynolds recalls a filament of dye-changing character in a glass tube. Froude recalls ship models moving through a towing tank. Strouhal recalls a wire producing a tone in moving air. Prandtl recalls a 10-minute presentation that separated an outer flow from a thin, viscous region near a wall. Nusselt and Sherwood reveal the parallel structures of heat and mass transfer. Ohnesorge and Taylor bring the listener to liquid jets and deforming droplets. Weissenberg and Reiner show that some flows cannot be understood without material memory and observation time. The history also warns against treating scientific names too literally. The person whose name appears on a number may have established the underlying experiment, developed part of the theory, supplied the notation, organized its engineering use, or been honored only later. Discovery, formulation, naming, standardization, and popularization are different historical acts. The dimensionless language emerged through all of them. The people encountered here helped build fluid mechanics and transport phenomena from the 18th through the 20th century. Much of their work addressed ships, pipes, sound, heat transfer equipment, atmospheric motion, droplets, and industrial processes at visible scales. Modern fluid mechanics also operates in channels narrower than a human hair, around particles and droplets comparable with cells, and inside devices small enough to perform analytical procedures in the palm of a hand. That change is not merely a reduction in size. At sufficiently small scales, the hierarchy of physical effects reorganizes itself. Inertia often recedes. Viscosity, diffusion, surface tension, capillarity, and interfacial chemistry move to the foreground. The governing principles remain connected to classical fluid mechanics, but different terms and boundary effects become dominant. That is the world the next chapter enters.